We are here today to talk about von Neumann algebras, which is a very esoteric thing. And I would just like to kind of give an overview of what they are and what properties they have. And maybe you've heard of these three types, and I would like to motivate why there are only three types. And so the agenda is first we ask what is a von Neumann algebra, then to which types are there, and then at three there is a question, like usually we want to talk about like entropy and information and things like that, and there is a point that in these type 3 algebras you can't really do that very well, so there's no real notion of entropy, and I would like to motivate why there are no traces in type 3 algebras. So basically no standard quantum information. And in 4, if I manage to do that, I will describe how this language helps you, for example, to give a rigorous definition of a thermodynamic limit of a system, basically. Which is a bit different from what I talked about on Thursday, but kind of, I think it's, to me, like, I think of this more as a conceptual thing because I'm not a mathematician. I don't prove stuff, but I think conceptually it makes things very clear what it means to take a thermodynamic limit, for example.
Before the traces and
why no traces in, that's a note. No traces in type 3. And then I will describe, thermodynamic limit and what is called the GNS construction. Hi. Good. So, we start with the question, what is a von Neumann algebra? So, one, what is a von Neumann algebra? And for that, I first define what is an algebra. So an algebra is just a set S where I have elements such that sums are in that set. I have a multiplication and I have a scalar multiplication. So for all alpha, for example, in the complex numbers, I will always look at algebras over C. So yeah. At least, okay, no, in algebra you don't need the scalar multiplication for that, but for the purpose of this talk, I will just include scalar multiplication. So it's basically a vector space with a multiplication between elements. Then star algebra. A star algebra is an algebra with an involution. An involution is a map dagger from S to S such that alpha A dagger is alpha complex conjugated A dagger. So, for example, the standard taking the adjoint of an operator, that's called an involution. So matrices form an algebra together with the involution, they form a star algebra. And then at last, now, so the point is, this is all abstract. We don't need a Hilbert space for that, for example. And this, you can just think of like star algebras as abstract sets that you can multiply, add, you have some notion of involution.
yeah, vector.
No, the algebra itself is a vector space, but they don't need to act as operators on a vector space. That's what I mean. And then we have C-star algebras. Those are star algebras together with a norm such that the norm of A dagger A is equal to the norm of A squared. That's called the C-star algebra. And also for C-star algebras, you don't need a Hilbert space or anything. These are just like objects that exist abstractly, and there's no intrinsic notion of Hilbert space. You can represent them usually as operators on Hilbert space, but you don't need them for the definition of them, kind of. So this is sort of the base layer of information that you need. And for example,
a short question.
Yeah.
Do you need completeness for C-star algebras?
Sorry. You need, so C-star algebras, you have a norm, and the algebra is also a Banach space, so it's complete in the norm topology. Yeah.
Okay.
So C-star algebras are Banach space. That's also true. So overall, most of what I will say is approximately true. It will usually not be exactly true, but it can be made true. So the example for a C-star algebra is B of H.
Wait, what norm is that?
No. And C-star algebra is just an star algebra with some norm in which the algebra is complete. And it has the C-star property. That's called the C-star property. So it's just any algebra that has some norm. The example, for example, B of H, like all the bounded operators of some.
As long as that property goes for any norm in your space, this is a C.
No, the C-star norm is unique, actually. So usually given an algebra, and so I think it's so given an algebra and a norm, there is only one norm in which it's a C-star algebra, basically. I think
it's always basically.
If you have a Hilbert space for it. You don't need so. Yeah. Yeah.
So that means this A dagger A norm property only holds for one norm.
Sorry again?
A dagger A norm equals A squared only for one norm.
Yeah. It's the thing that is unique by your algebraic structure. And so an example is B of H with the norm as the supremum over all vectors. So given a Hilbert space H, you just take the supremum over all normed vectors, and you just compute the norm of this object, and the supremum of all these numbers, that's the operator norm. Finite dimension, it's the largest singular value, blah, blah. So that are C-star algebras. And now the question is, good, what kind of object do we want to, hi. Okay, then, good. Some more people come. Hello. Okay, great. So you haven't been smart. So basically, to summarize, this is the plan. And then I started writing down definition. What is an algebra? Stuff you can add and multiply. You have some scalar multiple. A star algebra is something with an involution, which is like taking the adjoint, which is an antilinear map. A C-star algebra is a star algebra where additionally you have a norm such that the norm satisfies this property. These are things that don't need a Hilbert space to exist. Right? And an example for a C-star algebra is just the bounded operators of some Hilbert space with a standard operator norm. So now, what?
So doesn't norm on the vector need to use scalar product?
Yes.
Yeah. So then I can remind you of last. So this is first abstract, and now you can ask physically. Okay, assume you have some world, or say you have a lattice or so, and you take a region in that lattice, and you ask sort of, okay, I have some guy sitting here, and he has access to that. What sort of what objects should I so what are the operators that he has access to, or she? And thing that I motivated last Thursday is the following idea, is that just assume, okay, forget about the lattice, because in a lattice it's kind of trivial, but assume you have some continuous space-time, you have take a region, and you ask, okay, I have some guy sitting here, and she's making measurements. She has access to some kind of finite energy calorimeter that can only measure up to some energy, but then she can increase the maximum energy she can measure. So she has kind of access to some set of operators On, which, so for example, measure energy up to some specific energy, and otherwise they are not sensitive to it. And what it means to have access to is kind of have access to expectation values. Okay, and we say that the observer has access to an operator O if kind of the observer has access to stuff that approximates it in the sense of matrix values. So we say that someone has in principle access to O if he has access to a sequence of operators such that all the matrix expectation values go to 0 if you approximate higher and higher. Okay, and this type of convergence is called convergence in the weak operator topology, or WOT convergence. And so this is why I now will start talking about the weak operator topology, because it's kind of a sensitive notion of kind of you have access to some stuff, but you want to include everything that you have in principle access to. And this is a very weak notion of having access because it's kind of only in matrix values, in matrix elements. There are stronger notions of convergence. So then an actual question is, given access to some set, to some subset of the bounded operators, B of H, such that it's self-adjoint. So I have, for each operator I have access to, I also have access to the adjoint. What is sort of the closure of this set in this weak operator topology? So what is like the set of all operators I can approximate with the stuff that I have access to? And this is what one will then call sort of the algebra of observables that the person that has access to S has in principle access to, or just the algebra of observables. And to say how to get it, there's a nice trick. So Friedrich last time talked about 3 topologies. He talked about more, but there are 3 natural ones on the set of bounded operators of some Hilbert space. So now we want to have something that lives in a Hilbert space. The first one we found already, that's the norm topology. Stuff converges in the norm topology if the norm goes to 0, which is a very strong thing because you kind of need to have control about all vectors in your Hilbert space essentially, and not just single ones or single matrix elements. Then there's the strong operator topology. There you say On converges to O in the strong operator topology. On minus O applied onto some vector goes to 0, but that it goes to 0 for all vectors. But it can go to 0 with different speeds for different vectors. Okay? And then the weak operator topology is exactly the left thing. It's On minus O, that matrix elements goes to 0. For all tuples psi. So now we want to kind of have the weak operator closure of a set of some observables. And the question is how to get it. And there is a theorem that you need to be very smart for to find it, because von Neumann did it. That's the, first I need the commutant. So given a set S, a set S, the commutant of S is just the set all operators that are bounded such that OS is 0. So it's just all operators that converge with that commute with S. It's just essentially if I have a lattice, right? If I have a lattice, I don't know, here, and I look at this region, then the commutant is just all operators that act on the right side. Basically, that's the commutant of the operators on the left. And so for Neumann's bicommutant theorem, says the following, that given a self-adjoint set S, of bounded operators, then the following are equivalent. The bicommutant of S is S, so all the stuff that commutes with the commutant is itself. And S, some self-adjoint set satisfies this exactly if S is SOT closed. Where closed means if I have a set of operators. So if I have a subset, a sequence in S that converges in this way to some operator O, then O is also in that set as well. That's what closed means in this sense. And this is also equivalent to S being weak operator topology closed. So these things are when you are asked to kind of self-adjoint or like I think just self-adjoint sets, it's all the same. So in particular, given some set S that is self-adjoint, you can just take its bicommutant and then you just get its closure automatically. For that, you also need something like S prime 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 as always. So sort of then you can repeatedly show that. Take S, take mathematically its bicommutant, and you get its closure. So if you have some set of operators, you just take the bicommutant and you get all the stuff that is in principle measurable. So now we can define a von Neumann algebra. So definition. A von Neumann algebra, M, is an subalgebra of the bounded operators, such that M equals to M dagger, and M is equal to M prime prime. So that's just, this is what the von Neumann algebra is. It's just the weak operator closed algebra. So now we know what they are. Now we can define two other things that are important. So the first is, so maybe I should get an example. I will first define things and then I will give an example. So another thing that is important is called the center. The center of some von Neumann algebra M is just the intersection of M and M prime. So it's all the stuff that is in M, but that commutes with everything in M. So for example, the identity is in that always. Okay, and the question is, for example, is there more than the identity that exists in that center? So this is the center. And in particular, you define a von Neumann algebra to be a factor if its center is just the identity times complex numbers. Okay, so that's what's called the factor, and this definition makes sense because the paradigmatic example, take a Hilbert space that you can tensor factorize, and you look at the algebra that's just acting on the left system and doesn't do anything on the right system, right? Then its commutant is the identity on A tensor B of HB. And the center of M is exactly the identity times complex numbers. And that's why it's called a factor, because these algebras come from acting on just one tensor factor. Okay? So an example of something with a non-trivial center, for example, is you take a Hilbert space H, which is a direct sum of smaller Hilbert spaces, where each of them is, say, also has a factorization like that, IV. So you just have like a sum stack of vector spaces together, and you look at the algebra that acts always on the left system of each sector. So you look at M, again, is the direct sum of B of HIA tensor the identity B. And then you can convince yourself that prime is exactly the thing the other way around. You do nothing on the left, and you do something on the right. And then the center is the direct sum of the things that are identities on each sector. But the point is they don't map between sectors. Okay. So this is a non-trivial center because you can have kind of a different multiplication in each individual set. So this is a non-factor algebra. Okay. But we usually only care about factors because there's a theorem that I never looked into the proof in, and but that is very powerful. That says, given a von Neumann algebra M, there exists a decomposition such that M is an integral over some, basically over R, with kind of, you have just the sum over individual algebras, and the M lambda are factor. So kind of you can write every von Neumann algebra as an integral of factors. And in particular, when it acts on a Hilbert space, this also induces a decomposition of the Hilbert space into an integral of Hilbert space. So that's a general thing that's true. What? I cannot define it to you, but you can think of in a separable Hilbert space, usually it will be like a sum. Here, you have to define a measure. I can't tell you how the measure is defined. The point is, there exists such a decomposition, so you can just care about factors and study them.
You would put some data distribution in there if you make the direct sum?
Yeah, so this is a measure. That's not just the
Just
yeah, exactly. If you have a direct sum, you put this would be some data distribution measure also. But in general, for all Hilbert spaces, you can prove there exists such a decomposition, and each of the things here is a factor. Okay, so in the end, you can always decompose every von Neumann algebra into factors, and you therefore just study factors to get to work. Now I don't have space anymore. But do you have questions so far? No questions.
With any relation to the type of von Neumann algebra and the whole space lives on, and this integral over this direct sum integral.
So every factor itself has a type, and in that this is called the central decomposition, and in that can appear everything. But you would say if every factor in that decomposition has the same type, then the whole algebra has the type.
Even if it's an uncountable direct sum. And
I think so, but I mean that's an area of the literature I will never visit. So I hope. So as I said, everything I say is approximately true and not should be taken with a grain of salt. I mean, you can make everything I say precise, but I am not in the business of precision. So then we can now tell you what is a type, luckily. And that is, for that I have to motivate why you care about projections. So we do now it's called the Murray von Neumann type classification. This was introduced by Murray and von Neumann in the 30s of the last century. And they thought that this part of it is irrelevant, but it turned out to be wrong. So what is like the minimal object you need to study to understand what is possible? So first of all, take any operator that is bounded. You can always write it as a sum of self-adjoint operators, okay? And we know that where A, B self-adjoint, so A is A dagger. And we know from the spectral theorem that every self-adjoint operator you can write as sort of dp lambda, where dp lambda is a projection valued measure. So for example, usually we kind of have operators that are discrete in a sense. There you just sum kind of over the eigenstates of them. But in general, if you have kind of a continuous spectrum, then these measures appear. Okay, but the point is that every operator is sort of a sum of projections. So essentially, you just care about the projections themselves. If you classify what kind of projections your algebra has, a different maybe. If you know what projections your algebra has, then you kind of know what algebra you have, because there's a theorem. A for Neumann algebra is the norm closure of the linear span of its projections. So this kind of is the exact statement that tells you you only care about the projections, and then you know what the algebra is.
With projections you expect to try.
So projection, okay, so definition, sorry. P is a projection. So if P is a bounded operator, P squared is P, and P is equal to P. That's a projection. That's it. That's what a projection is. Self-adjoint operator. So for example, P equals psi plus phi, where phi and psi are orthogonal. That's a projection, right? Yeah.
Why does P have to be bounded?
Because so a projection, you always think of something that you have a big Hilbert space and it projects you onto a subspace.
Okay.
So it has to be smaller than the identity. Okay. In particular, there are operations on projections. Like exactly, that's a good point. So a projection, what does it do? A projection just is something that you have a big Hilbert space and it just projects you onto a set. So in particular, for every projection, so first of all, the set of projections I call P. Okay, let's be careful. Definition. M is a von Neumann algebra. The set of projections that are in M, we call P of M. Okay, and yeah.
Sorry, I don't want to derail this. I'm curious. The standard story in finite dimensions say P squared is equal to P that forces your eigenvalues to be 0 or 1.
Mm-hmm.
So does it mean in infinite dimensions that this condition does not imply that P has to be bound?
Sorry, why does that? Again, so you're asking, are there? Yeah. I guess so. Yeah, assuming that the operator has this, like maybe it does. It makes a lot of sense, right? Because if you have an eigenvalue, then definitely. But the question, I don't know. Maybe you can.
You just ask whether that's easier.
Yeah, I guess. Yeah, if it's it's self-adjoint, and then you have a spectral decomposition, and then sort of your eigenvalues have to be 0 or 1.
Right.
So it's fine.
I mean,
So these two would imply that P.
I think so. Yeah, that makes sense.
I mean, in general, if you think about projections, they if P is not P dagger, then they don't need to be projected orthogonally onto the subspace. If P is equals to P dagger, then they are projected orthogonally. This is how you can distinguish them, I think.
Yeah. So I take this definition for a projection and then I run with it. A projection, you can, a projection always implies a decomposition of your Hilbert space into kind of the image of P and the direct sum of the image of 1 minus P, okay? So sort of given a projection, it always is in one-to-one correspondence with the closed subspace of the Hilbert space. Okay. And now you can imagine you have kind of nice operations on that. You can take two projections that sort of map onto different subspaces, and you define a new projection that is the union of them that kind of that projects onto the direct sum of the two subspaces. Okay, and similarly, you can define the intersection, which is the projection onto the space that they have in common. Okay, so you have these kind of set operations on projections, and good. Now the point is we want to classify algebras. We need to know what kind of projections there are. And in particular, you want to kind of restrict the set that you care about. And for that, one has the following intuition. So let's take psi one projection, P1, and then you take P2, which is phi. They are both one-dimensional, right? They are, in a sense, the same up to kind of the rotation of the basis. So in particular, you only care about sort of projections up to some isometry. So one makes a definition. First, we kind of need the notion of a partial isometry. So do you all know what an isometry is? Okay. A partial isometry Pi is a map P of H to H, exponent, blah blah, such that U on the orthogonal complement of its kernel is an isometry. So what does it mean? I have some operator U. It maps vectors to vectors, but some vectors it maps to 0. All the vectors it does not map to 0. On them it is an isometry. Okay, it's kind of restricted on the set that it does not annihilate. It is an isometry. In particular, theorem take a projection in any for Neumann algebra. From that, it follows that there is a partial isometry, some partial isometry U, such that P is equal to U then. Okay, like that's essentially what a projection is just something that kills a subspace. Where did I draw that? Right. It's a projection. Hilbert space always kind of decomposes into the image of a projection and its complement. And sort of the projection here, you can make a map that kind of maps all of those to 0. But here is a unitary from the space into itself, and this will be exactly such a partial isometry. You can also take the identity in that space. This will also be the partial isometry. And so every projection you can decompose in this way. Okay. And in particular, one defines an equivalence between projections. We just said we want to kind of consider projections that have the same dimensionality as the same. Okay, so given for Neumann algebra A, and two projections. Yeah.
Can I just ask about the theorem before? Can you just take U equal to P again? So projection is also partial isometry, isn't that?
Yeah. You can. Yes, you can.
Okay.
That's actually what I sketched when I said that. And two projections P and Q. Then we say P is sub-equivalent to Q, or we write P is sort of such a sign. I'm always, yeah. we say that they are sub-equivalent if there exists a partial isometry U such that yes that we have, so we say that P is, it's like a smaller sign, but it's like smaller up to an isometry essentially. We say P is sub-equivalent to Q if you can write P as U dagger, but U dagger U is smaller than P. Okay, that just tells you that they are the same up to kind of a basis change. And then you call P sub-equivalent to Q. But in particular, for Neumann algebra, you only care about the partial isometries that exist in your algebra. Okay, so with regards to kind of the operations that you can perform, those are the same. And now there you can then also define an equivalence relation between isometries. You define two projections to be equivalent if P is sub-equivalent to Q and Q is sub-equivalent to P. Okay, so this kind of just tells you, okay, we only care sort of the kind of projections we have in our algebra, and then in the end we will classify the algebras by the kind of projections they contain. And in particular, one can show that this thing defines a partial ordering on the set of projections. And this equivalence really is an equivalence relation. Relation on P of. So this is really a nice definition of, yeah.
Maybe the terminate question, but what does it mean to dagger U less than Q? I mean,
it means that this just means Q minus U dagger U is positive. So if you take matrix value, expectation value, this is smaller equal to 0. Interesting. As a projection, it just tells you sort of it is a projection onto a subspace. Like here, you take as the whole space, like H, the projection for H is the identity, and you take any other projection, and P will always, the image of it will always be smaller than the identity in that sense. So it's kind of a projection is equivalent or sub-equivalent if it's kind of, you can map it to something that maps into a smaller subspace, the other projection.
And why can't you find a rank and be done with all that?
Because I will tell you now.
and 19.
Sorry? Yeah, that's exactly the problem. You would like to, but we do not live in finite dimensions, so at least I don't. So I think in the book where I learned this from, this issue is called in the book for Neumann also called it like the characterization of the infinite or something like that. So we'll come to that now. So we care about projections and we care about equivalence classes of projections, but they are equivalent with respect to the algebra you consider. Okay, so sort of your algebra tells you what stuff you can consider as equivalent and what not. Can the people online still read what is written on that thing here, or do I have to clean really?
You think this works? Yes.
Okay. Good. Yeah, so my main goal is to just tell you about the type classification and everything else that we can see how far we get. But now, right. So we can have a simple, so as Leonard said already, for finite dimensional, if P is finite dimensional, you can write P as sort of the sum over I equals 1 to rank P, and then onto some vectors. Okay? And in infinite dimensionality, there something funny happens, where a nice example you can look at. So consider the space of square summable sequences, right? Your space is just x1, x2, such that the sum of the xi squared is smaller than infinity. And that's the standard example of a Hilbert space. And now look at the partial, like now you consider as P1 is the identity, okay? And P2 is the projection onto all vectors that start with 0 and then have something in the next registers. Okay, and now I want to show that those are equivalent by giving you the partial isometry that does that. You define U of x1, x2 as the left shift, x2, x3, and you see then that U dagger of x1, like U dagger is then the right shift, okay? And you see U dagger of x1 is just the thing itself. So U dagger is the identity, but U dagger U, in U dagger U, you shift first to the left and then you shift to the right. That fills this register up with a 0 of x1 is exactly 0 x2. So you see that under this definition, the identity and P2 are equivalent. So you see that in infinite dimensions, like the stuff can be equivalent to something smaller. And that's the root of all evil for us. Yes. So now you can define a bunch of things. Maybe what kind of projections are they? So the first thing you want to define is something that is kind of a rank 1 projection. And the algebraic way to define a projection like that is so a projection in your algebra is called minimal. Exactly if essentially P is one-dimensional. Then, so a non-trivial example of a minimal projection is consider this operator, but then look at the algebra that it spans. The algebra that it spans is just all the stuff you get by multiplying that thing with itself. Okay, but this thing multiplied with itself will always give you a rank 2 projection. Okay, but the point is now that with respect to the algebra, you see these 2-dimensional space as kind of a 1-dimensional space, because the projection that you use just sees the combination of the two, but it can't kind of resolve that you actually have 2-dimensional space underlying. So if you look at the algebra generated by this thing, this is a minimal projection for this algebra, because the algebra doesn't contain anything that's sort of like a poly X or something. It doesn't contain something like that, because you just look at stuff that kind of has this as the base projection. Okay, so this is sort of a non-trivial example of a minimal projection. Okay, now you call 2. We just said that, okay, for finite dimensional projections, they are always like, they have rank 3, and they will be equivalent always to rank 3 projections. Okay, so kind of a finite dimensional projection is never, like a 3-dimensional projection is never equivalent to a 2-dimensional projection. Okay, so one defines a projection P to be finite if you have a different projection that is smaller than P, and P is equivalent to this smaller projection, that this implies that P and Q are the same. So this is sort of the algebraic way of saying, well, you can't kind of change, like finite rank projections are only equivalent to finite rank projections of the same rank. It's saying if you are equivalent to something smaller, then you have to be the same. That's why they are called finite. But note that this is always kind of, the equivalence is always sort of with respect to the algebra, because this equivalence relation always only contains the partial isometries that are in your algebra. So you can even have a finite projection that has infinite rank if your algebra is appropriate. Then there is, so this was finite, this was minimal, and then we have three, sorry? How much time do we actually have? Okay. So I do 1.5 hours. We started at 4:15, so I go on to 5:45. So a projection is called semi-finite if you can write it as P is the sum over I of Pi, where all the Pi themselves are finite. Okay, so semi-finite just means I can write it as a sum of finite stuff. Good? No, just a sum. It's think even counterfinite contains finite. Yes, yes. A finite, yeah, exactly. So and now you get to I will just do purely infinite. So then 4. So you call a projection P, it's not purely infinite, but if is purely infinite if there is no non-zero finite projection Q that is smaller than P. Yeah. So exactly. So this is always a statement with respect to your algebra, Q in M. So like if your algebra doesn't contain a finite subprojection, then you call this thing purely infinite. Okay. So if your algebra only contains infinite dimensional stuff and you have nothing that is sort of finite, then this object is purely infinite. And now you call a von Neumann algebra. A von Neumann algebra is called finite, semi-finite, infinite if the identity as a projection is the subproduct. So if the identity is finite, then you call the von Neumann algebra finite. If it's semi-infinite, then it's a semi-infinite, semi-finite von Neumann algebra, blah, blah. And the nice thing is that these properties like finiteness, they are preserved under these operations that I already erased. Like if you take the union of finite projections, you get also a finite projections. I think if you take countable unions, you also get, if you take intersections of finite projections, you also get finite projections. And it's a structure that is stable under these kind of operations. Yeah.
Can you make a simple example on
a simple
confused with the identity?
Yeah. Okay. So that's okay. That's I can't without the spin chain pictures. Like these are very unintuitive things. Unfortunately, I don't have a good intuition. Like
So
yeah.
even if the hyperspace is infinitely big,
The identity is,
It's not necessarily, the identity is infinitely big, but the algebra is not necessarily.
yeah, so B of H, right? You can write the identity. The identity is always sum over I psi psi. So it is a sum of finite projections. So in that sense, it is semi-finite. Okay. But it is not purely infinite. I don't have a good intuitive way. Like, if I will have time to talk about these spin chains, then I can tell you in the spin chain thing, but
Then do you need non-separable limits?
no.
Is a reasonable physical interpretation of this the low energy sector of an infinite machine? Because there you integrate out all the high energy momentum modes and you only stick to the low energy subspace.
I can't tell you that now, maybe if we talk, but I think in the spin chain, like after I tell you what it is with the trace, it makes a little bit more sense, but it's still abstract. I can't tell you now if I can give you an interpretation of it. Like, these things are fairly unintuitive, I would say, but at least sort of you can think of an infinite projection as one that is not finite. Right?
But I mean, like, the point here is that you don't occupy the entire Hilbert space, right? You're only concerned with like some subspace.
You're concerned with the subalgebra, yeah. You're not concerned really with the subspace, but you are concerned with sort of what resolution does the operators that you have, what can it resolve? If you're like this is do I still have it? So this thing with 2, that is a rank 2 projection, right? It can't resolve that you have rank 2. It itself sees only kind of the space that is the like phi 1 plus phi 2. If you take products of this thing with itself, you can never get just one of those. So the algebra that this projection spans only sees sort of this rank 2 space, but itself can't do any internal rotation. So the algebra it spans is still one-dimensional in that sense. So yeah.
I'm still trying to get a physical picture of what's going on. I mean, you're saying that there's no local transformation between phi 1 and phi 2.
There is no local transformation from the perspective where all the operations you allow are built out of this projection. It's like you only allow kind of someone to measure is the particle in the space that is spanned by those, but not in which space exactly.
So these are projectors onto like super selection.
For example. But
okay.
Yeah, you can consider like a single super selection sector.
Okay, so semi-finite is basically just the super selection sector within your entire Hilbert spaces.
Yeah, you can think of it. Yeah. Good. So now, you can call these von Neumann algebras like that. And now we can come to the type classification. Namely, the definition, a von Neumann algebra M is called, so type 1. If every projection of M contains a non-zero minimal subprojection. So what does that mean? It just means that sort of like the easiest example are always these direct sums of stuff. Like if my algebra is B of H, okay, I just take my algebra to be all operators, and I look at the projection that I just had. Psi 1 plus psi 2, psi 2. Then I have this thing is a subprojection, and this thing is a subprojection. So in this sense, like no matter what projection in B of H you take, you can always find rank 1 subprojections. And because of that, it's type 1. Type 1 algebras are ones where you always have kind of where every projection is built out of kind of discrete minimal stuff. Okay. Then it's called type 2. If it is semi-finite, so the identity is kind of a sum of finite projections, but none of the finite projections are minimal. So kind of these are algebras where you don't have these types of stuff where you also contain these guys. You only have things that are sort of infinite dimensional intrinsically. But it's still semi-finite. So it means you still have like these finite projections that are kind of have a certain not infinite size in a sense. But in what sense I will tell later. So and it's called type 3. If it has no non-zero finite projections. So this is just like by exclusion. Like the standard thing B of H, they are type 1 because they have projections onto one-dimensional spaces. Type 2 things are kind of sums of finite things, but the finite things themselves are not rank 1. And in type 3, everything is lost. You have kind of no nice structure. These are like, von Neumann initially thought that they are useless, but then it turns out that all quantum field theory have only those, not only, but mostly those. So they turned out to be useful. Good. And now the last thing about the type. This will have a, I can still put that in. Then there's a theorem. If you take any von Neumann algebra, then there are, so you remember the center, that's all the stuff that commutes with everything in your algebra. Then you have a collection of projections, P1, P2, 1, P2 infinity, P3, that are central. So they commute with everything. So in this picture where your Hilbert space kind of has this direct sum structure, HI, you can think of those like P1 kind of projects into a subset of those, then P2 projects onto a different subset of those, and so on. But they all are kind of just a projection onto the individual Hilbert space, but they don't act inside the Hilbert space itself. Okay. So the theorem just says if you have a von Neumann algebra, there are such projections such that you take your algebra and you multiply it with the P1. And this algebra is type 1. Then you take the MP2, and then I will say what the difference is between them. And then this one is type 2. And MP3 is type 3. So in that sense, like it's a by exclusion, and that's why there are only 3 types, because the third one is everything that the first 2 are not. And every von Neumann algebra kind of can be decomposed into a direct sum, essentially, of them, and they are all of them. I can sketch the proof. Yeah, I can sketch the proof.
I've one short question. Here you give this characterization in types. Actually, when you wrote down von Neumann algebra is called finite, semi-finite, infinite on the right board, I thought this would be the characterization. Is this also a characterization that you wrote down on the right side? Like every von Neumann algebra is either finite,
Sorry. No. This just tells you if you have no. if a von Neumann algebra is finite, then it is also type 2. But this is a statement given any von Neumann algebra, you can decompose it into a sum of algebras that have a fixed type. That's the difference. Like, this is kind of the statement, sort of, the whole algebra is finite, but this is the statement for every algebra you can, if there exists, like, there is a unique subalgebra that is finite. Like,
they can also be.
this is a decomposition, and this is just if you don't need the decomposition, basically.
Okay, thanks. To get the connection. Thanks.
Yeah. Good. So the sketch of the proof is depends on what you understand as constructive. But it's maybe nice to know why it is true. So yes. But like, I hope after this kind of you have the minimal knowledge of why there are 3 types. This is my main point, I think, today. But the idea of the proof is just define P1 as the supremum of central minimal projections. Okay. So like, this is the largest central projection that is minimal, and that you call P1. And then you can show that exactly MP1 is type 1. Exactly because it has minimal projections intrinsically. Kind of by taking the supremum, you have taken all of them with you. Okay. Then you define P21 as the supremum of central finite projections Q that are smaller than 1 minus P1. Okay, so you've thrown out everything that kind of is type 1, and then you look into that subset that you are left with for everything that is finite and central. And then P2 infinity is also the supremum of all everything that is left after this thing, 1 minus P2. 1. And P3, you just define as 1 minus P1 minus P2, 1 minus P2 infinity. So this is kind of the idea of the proof. You just have to show that this is enough that it has all the nice properties that it's supposed to have. But sort of, it's just like you always throw out everything you have already taken care of that. You take the maximal thing that has the property you wanted to have. And that's why also there are only, yeah?
Well, one detail here, a bit confused because you go the same step from P1 to P21 and then again to
okay, sorry.
To infinity. So what
here,
if you
okay,
what if you repeat the step again?
Sorry. So you take all the projections that are central and finite, and and here they don't have to be central.
Okay, because
the thing is, one can then show that the supremum of that thing is again central. So, but we won't prove that. But the point is, like, forget about this distinction. The point is, like, you can always find a decomposition of any algebra into these 3 things. Okay. And now we can start with quantum. So this is, I think, the base layer that one needs to know, and everything else is plus. I have still 25 minutes left. I think something I should manage to do. So at the next thing, I want to say why there are no traces in type 3 algebras. Because I think that's an important question for us, because you people like quantum info, and for quantum info you like entropies, and for entropies you need traces. So it turns out in these type 3 algebras there are no traces that are useful. So quantum information is very hard if you have these things. And that's also why quantum information and quantum field theory is very hard, because there you only have type 3 algebras. Not only, but the things that people care. Now we want to say why there are no traces. So are there questions until now? So that's the statement that I want to motivate. So what is a tree? Yeah.
So the phenomenon algebra is property that the commutative of the commutative, right? How does all this projector type business relate to that property? Like if
you use it in proofs to kind of say that things turn out nicely. Like the thing is that the bicommutant makes it closed in the weak operator topology. So usually, like you take things like the supremum, right? You need to show that the supremum is always again in your algebra, and for that you need something like this closure property. Like if your algebra is not closed in some topology, you can't really take limits. So you need and the point is these. The bicommutant theorem, it's the same as the strong operator topology and weak operator topology. So it's kind of the minimal thing you can take, really, is closure. But it just turns out that because you have this closure property, you can take things like suprema and they are still in your algebra. But, yeah, so why there are no traces in type 3? So look at the standard trace in the Hilbert space. So we said in the beginning, every operator you can write as A plus IB with them self-adjoint. So if you want to compute a trace of O, you need the trace of A plus I times the trace of B. So now you want to know how do I compute that thing for an operator. Now, forgetting about this compactness thing that Friedrich talked about last time, you take a self-adjoint operator and want to compute its trace. Then you decompose the operator into its spectral decomposition, right? dp lambda times lambda. And then you use linearity and you take out the integral, integral lambda trace of dp lambda. And this is the trace of a projection. So this is just the dimension of the of dp lambda, basically. So a trace, if you have a function that counts dimensions, you can define a trace by this logic, essentially. You just, given a projection, you want to know how large it is. And the point is that traces have this property, AB equal to trace of BA. What that tells you is that if you have a projection, trace of P, we say we can write it as kind of U dagger for some partial isometry. But that just makes it to trace of U dagger U. And this is like, if P is equivalent to Q, then we call it. And like the point is equivalent projections should have the same trace. Okay. But in particular, you want then if a trace should kind of have a dimensionality associated to it, then these infinite projections are bad. Because we just saw an example sort of where an infinite projection is equivalent to a smaller one. So you don't want a trace to have a finite value on an infinite projection, essentially. So you have three properties that you want a trace to have. You call a trace, or a trace state, any function. Trace, it's like the definition that I do now. A trace is a function from the von Neumann algebra to the complex numbers, such that you can define it on projections. It's linear, okay? And on projections, it should have, okay, it should also be cyclic, so trace AB equal to trace BA. And on projections, you want to have the following thing. One, if two projections are orthogonal, so like they map onto orthogonal subspaces, then the trace of kind of the union of them should be the trace of the sum of the traces. Because kind of if you take the trace of orthogonal spaces, that just decomposes into the sum, right? Then the second is that if P is equivalent to Q, then it means trace of P is equal to trace of Q. And the third thing is, we just said, okay, this is something you want to have you want a trace to have, But in particular, this kind of forces upon you, it should only be finite on finite projections, because only they can't be equivalent to something smaller. So trace of P is smaller than infinity if and only if P is finite. Okay, that's the thing that you want trace to satisfy. And now the point is, already you can answer now the question why there are no traces in type 3 vectors. They don't have finite projections. So it doesn't make sense to ask for a finite, like you can't define something that has this kind of dimension counting property without breaking things, because they are equivalent to smaller stuff. So this already excludes essentially type 3 vectors to have a trace. And now there is a theorem that tells you given a semi-finite vector, so you care only about vectors because we said before you can decompose everything into a sum of vectors, and then you just define the trace by linearity, essentially. So you only care about vectors. Given a semi-finite vectors, there exists, you can define it, a function b that satisfies the above. And in particular, d is unique up to constant multiple. What this means is, for example, I can just define a new, given like the standard B of H thing, I can define a new trace, d prime of psi that is just, say, 2 times trace psi. And this is just multiple of the standard trace. Okay, so there's really just the standard trace that we use is kind of normalized so that minimal projections are mapped to 1 because they have 1 dimension. Okay. Yeah.
Yeah. Okay. Just to get to the if I just operator. Operators would by your definition also not have trace. That the concept because
No, the bounded operators are semi-finite. They are semi-finite. B of H is semi-finite. The identity.
Define an operator. So
Again, sorry. Maybe I
want something that maps from like it's more about the concept. So if I have something that maps from my algebra to the complex number. If I define trace in a bounded operator, that could be infinite.
Yeah.
So it is not well defined for all.
Sorry. Yeah.
And then your argument doesn't.
Yes.
Yeah. But the point, okay, no, it has to be finite. Okay, so the point is, for infinite algebras, it will always map to either infinity or 0. And if you have a semi-finite one, you have one that gives you finite value for finite operators. But in a type 3 vector, you don't have finite operators, so it's either 0 or infinity. Like the 0 function also satisfies these things. And infinity also, like the sum infinity plus infinity is infinity, 0 plus 0 is 0, essentially. So yeah, if you want to do quantum info, you want to have type 1 or type 2 algebras. If you don't, then you have a problem. There are kind of things you can deal with, but you can't define an entropy. Okay. Yeah.
So the normal algebra is the
sub-algebra of the bounded operators.
For the bounded operators, I can define the trace.
Yes, but the standard trace for a type 2 vector will always give you infinity.
So the arguments we take bounded operators, like phenomena because are bounded operators, would in any meaningful way not have the standard trace. So the question of this entire thing is, can we find
a finite
anything else that at least pretends
to be a trace? Yes, exactly. Yeah. So I have much. Yeah. Sure.
I'm aware of the fact that there's no trace in type 3 and that there's no entropy also in type 3, but I mean, are there proxies for that? In the sense, because
entropy differences.
algebra or C star algebra, that expectation values are still well defined, and you can make operational definitions, and you can say, I measure something and I look at like Shannon entropies of distribution, and think of
So
observable methods that resemble.
relative entropy is defined, for example. You can define relative entropy, but the way how you see that the entropy is not well defined is you put the quantum field theory on a lattice where you it diverges as you take the cutoff to 0, and that's a sign of your local algebra being type 3 essentially. But the point is that these UV divergences that you have are universal. So if you take differences, they cancel out. Yeah. So
I mean, maybe a simpler way of saying this is just to take like an ordinary quantum field theory. I mean, like you always compute energy differences.
Then social information zone will also be perfectly well defined.
But mutual information is entropy 1 plus entropy 2 minus the 1, but you then I just mean like the mutual but in the mutual information you just subtract the entropy of the intersection once, right?
No, that's the initial.
Then
That's not what I mean. No, you do it twice. So that's
you do it. Yeah. Then it should cancel out. Yeah. Like the point is, you need something where you kind of cancel out all the UV divergences.
Yeah, okay.
And then these things are usually you can define them in an algebraic way.
Yeah. Okay. That is the case.
Sorry. You can define them with relative entropy. You can define without a cutoff. There is an algebraic definition for what a relative entropy is in a type 3 vector, where you don't need a cutoff for. Yeah.
Super, like, interesting that. I was wondering about this. Like, there's this thing where you, like, example, entropy of space-time, right? And I would presume that that's also kind of within this quantum field theory. So, like, for example, like in black hole, like, in essence, they're trying to compute.
That's okay. So, there are different answers to that. So the question is, how do you derive that formula? Usually, so one thing you can do, you can put in a cutoff, and then you can define this function. Like what people usually do is you have a region in space-time, you have a little bit of quantum gravity fluctuating, okay, and this thing has an area, and you compute the function a over 4g plus you have some quantum field here plus s out, and this doesn't make sense. That's an infinite thing. You put the thing you introduce a cutoff. With the cutoff, this is finite, and now the thing is you have to take the cutoff to 0. There's a conjecture that says that the divergences of those two cancel out, and you end up with something that is finite in the limit. And the question is, why do they is there sort of an algebraic way of seeing this? 3 years ago, Witten published a paper where he suggested that, I can derive that thing, and the way I derive it, I make the type 3 algebra into a type 2 algebra, and then I have a trace, and then I can compute the entropy, and this pops out. So there are different ways how you can arrive at this answer. Now there exists a kind of way of deriving that in this algebraic language, where the answer is that it's finite because it's the entropy for a type 2 algebra and not for a type 3 algebra. But I have one more thing I would like to say. That's 5 minutes, and then we can talk about this trace thing more, because I guess that's somewhat the most interesting for you info people. So what does that mean? You do actual quantum information. I just do fake shit. So
more magic than anyone.
So the last thing I want to talk about is the thermodynamic limit. So the thermodynamic limit and the GNS construction, that's one. And the question I want to ask is, you have a Hilbert space that is sort of a lattice system, KHI, and you take only n of them. And then you have a Hamiltonian on that system that also depends, like, I don't know, XY, Heisenberg chain or whatever. And now the question is, you can define a density matrix for Gibbs state, e to the minus beta hn divided by Zn, where Zn is the trace or the partition function, right? Now the point is, in the large n limit, this diverges. Okay, this is not a finite number. This doesn't have a finite value because this is something like the free energy is extensive, so it's proportional to the volume. If you take the thermodynamic limit, the volume becomes infinite, so e to something infinite is infinite. So these things are usually not like the question I want to ask is sort of I can formally, what does it mean to take the thermodynamic limit? Like what is the Hilbert space that describes the thermodynamic limit of a thermal state? Okay. And the way you can do it is via the GNS construction. And so I want to define a Hilbert space that describes the thermodynamic limit of a lattice system. And what you do is the following. You want a Hilbert space with some vector, it's called omega, that corresponds to the thermodynamic limit of the thermal state. Okay. So one can build it as follows. First, you define a vector, omega, that you just ascribe to this thing. Okay, you just define an abstract object that you associate to the thermal state. Okay, and now you have your operators in that lattice system. Okay, you have an operator that's a bunch of identities, and then you have an operator, and then you have again a bunch of identities. Up to some finite value. And now the thing is, if you grow the system by a layer, you can still identify it with an operator that sort of acts on the same part by just adding an identity here. Okay, so this way you can kind of define an algebra of operators that describe finite operations that is well defined. Okay, so mathematically it defines a C-star algebra, whatever. But now what you want to have is in that Hilbert space, you want to have states that describe the thermal state where you have acted with a local operator. Okay, so what you want for each such, I call that O hat, for each such O hat, you write down a vector O hat. Okay, and now you have a bunch of vectors, you can take linear combinations, blah, blah. Now you want to have a Hilbert space, so you want it in a product. So you define O hat prime, the inner product between such two states, just as the limit, as this thing goes to infinity, of the thermal expectation value. So trace e to the minus beta h n O hat dagger O hat prime. And this thing is well defined, that's well defined number, and that defines you an inner product. There's also something with stuff you have to quotient out, but I will not care about this. But essentially, this way you have a set of states where you have sort of a vacuum that represents the thermal state for the infinitely large system, and you have inner products that are well defined, and this defines your Hilbert space. And that's the Hilbert space that the thermodynamic limit lives. So this way, kind of this algebraic notion can give you a rigorous definition of what it means to have a Hilbert space in which the thermodynamic limit lives. Yeah.
Sorry, could you just briefly mention what you quotient out? Because
the ones that map to zero, essentially. Then so like you have this thing, and it could be, say, Hn has the vacuum state. No, it's bad. Like, okay,
let me just tell you the background for my question, because like normally when you do effective field theories, it's matter, like you normally want to integrate out some high energy momentum modes. And I'm just trying to understand what's the analog.
Yeah. Okay. So
I'm guessing it's what you quotient out by.
I think so. I would like to know if there's a more precise, like this thing just takes the infinite lattice in principle. Like the point is, what you quotient out are the things where this limit is zero. Okay. Then so if this limit is zero, then you don't care about these operators because they just are not visible to that state. Those are the ones that you mentioned. They are the high energy modes if you want, because if they kind of have very high energy, then this will go to zero. Okay. I think that might be a way to see that.
Okay. And there's probably some restriction on your Hilbert space that would allow this GNS construction to exist.
No. I have a sequence of lattice systems. I define a state on the algebra. I assume would measure that this is for a wide range of Hamiltonians, it's true, but this limit, if it doesn't diverge, you can define that, like your GNS interface always exists. As long as you have kind of this limit does not go to infinity, then you can define that.
From a physical perspective, for certain systems, it's tricky to write down a field theory.
I don't say that this gives you a field theory, right?
Yes, but I mean, like, you can't define a thermal state. Like, it's not going to be well defined for.
No, for like quantum field theories don't have there is no Gibbs state, right? That's exactly because the volume is infinite. But you can define the terminal expectation value still.
Well, you need to be careful if you have like some mixing between your lattice and restrictions.
Yeah, but
which is what people call UBI or mixing. So I think there's like some restrictions.
Well, it all depends on what this limit looks like, right? If there's something weird, some stuff diverges or something, then this will not define your state really. But as long as this limit is finite, there's no problem. So just define the limit.
So I have no background in this, so I cannot join this discussion. But I'd like to understand. So the Hilbert space becomes your algebra. You made those into vectors. What did you use the vacuum state for? It's not in the Hilbert space. Is it?
No. This one is this. Right. Good point. So I also want to represent those guys on the Hilbert space, right? And you just define then a representation for them. Essentially, if you act on the vacuum, you get exactly the one. Okay. That's a very natural thing then to do. You act with it on the thermal state, and you get the state that corresponds to what you get if you acted on it. Kind of an energy.
Yeah, again, another one.
Sorry?
You should act again with another one.
Yeah, it finds your star homomorphism of prime, and you have pi of O. Right. This is O prime times. Yeah.
This will always be finite because you're only finite. Yeah.
The thing is, you define a vector, assuming there are none of these weird ones that you caution out. You just define a set of all those vectors, and then you define the representation that way. And then the inner product is just always defined because I assume that this is just the way defined with. It doesn't diverge, I mean. But that's all I wanted to say today. I think this kind of gives you an overview. Wir haben Schluss. Ja?